All right, let's see. So, class. All right. So, for those people following along, yes, this is the homework right here, and I gotta unfreeze it so we can take a look at today's notes, which is 5.2 definite integral, where we are going to do Riemann sum. Riemann sum is actually what we've already did in 5.1, but we actually have a formula, a process for it, instead of actually trying to make it ourselves. So, let's see. Right here. Here's the example. So now this one right here, it says for the function right there, and partition the interval from 0 to 6 into 4 subintervals. Now, does it say equal subintervals? No. Are they equal subintervals? No, they're not. That's important. That's super important. That is something that a lot of people just miss. They don't read it. They don't pay attention. Do they have to be the same width? No. They do not have to be, especially when you're doing tables. They are not going to be the same width for each one. So when we were doing this the other day, I was referring it to a left hand or a right hand. Now today we're actually going to actually do the one with left hand. And someone also asked me about the midpoint, and I'll show you how to do midpoint. So technically, when we do this, each rectangle is going to be like this, where the distance from A to B is my delta x. It's going to be whatever the width of that rectangle is. Okay? Remember, delta x refers to the change in x. So there's my delta x. And since this one is going to be a left endpoint, all these ones are going to be f of A is going to give me this value from here to here. Does that make sense? How do I find the area? Yep, f of x times, or f of A times delta x, right? Or length times width, or base times height, right? It's just a rectangle. I know it actually is going to be super complicated, but it's just a rectangle no matter what. So left endpoint for each one of these means that I'm going to start over here, my left side. So what is my delta x there? How far is that? It's 1. Okay, so it's going to be 1 times f of 0. Why f of 0? That's the left side of the rectangle, right? Okay, plus, next one, 1 times f of plus, what's my delta x? 2 times f of plus, what's my delta x? Times f of and Riemann sum is going to be approximation of this, of the area under the curve. And at the end of this, I'll show you guys how to actually do the real area under the curve. So get the exact value. All right, f of 0. So this is going to give me 0 minus 3, negative 3. Plus 1 times f of 1. So that means that my answer is going to be plus f of 2. That's going to be 1 times 2 is 4. So that's going to be 16 minus 3 is 13 times 2 is. Add all these together and my total answer is. Now, we can identify a problem here. How do I have negative area? Perfect. Good job. The graph of this is under the x-axis. So right here for these first two, these are under the x-axis, so that gives me a negative area. Where over here, this is above the x-axis, and it's above more than it is below. All right, midpoint. Now, midpoint formula is actually going to be like this: a plus b divided by 2. So, still, delta x. What's my delta x there? Yeah, still 1. Times, now this is where the midpoint changes. So f of, so my a and b is going to be 0 plus 1 is 1, which is 1/2. There we go. Next one, delta x. What's my delta x? 1 times f of, so right here it is 1 plus 2 is 3. 3 divided by 2 is 1.5 or 3 over 2. I like leaving it as improper fractions because fractions are easier to square and to do all kinds of other stuff. So, yeah, we can plug it in easier too. So, if I was to have to square that, it would be 9 over 4, right? But if I had 1.5 and handy square 1.5, so 1.5 times 1.5 is exactly. 2.5? Yeah. 225. Yeah. Anyway, next one. Delta x is 2. F of 2 plus 4 is 6. 6 divided by 2 is 3. Delta x is 2. F of, so 4 plus 6 is 10. 10 divided by 2 is 5. Let's do each one. So f of 1/2. So that's going to be 1/4. 1. 11/4. Yeah, negative 11/4. 3 over 2. So that's going to be my 9 over 4. And then my negative 3 is negative 12, right? 12 over 4. Negative 3 over 4. Right, then 9 over 4 minus 12 over 4. Oh, yeah. What's that going to be? 6 and then multiply by 2, so 12. Yes. 5. 25 minus 3. Well, that wasn't multiplying. 25 minus 3, 22 times 2, 44. So combine my negatives, I end up with a negative 12 over 4, which is technically negative 3, right? When I combine these two, I get negative 3, right? Negative 3, and this is positive 9. Positive 9 plus 44 is 53. Now, let's say for instance, I pay attention and I'm not on my phone. Yeah. Negative 14? Oh, see? Thank you. Man, at least some people are paying attention. I just see people picking up their phone for some reason and not really even second guessing if I'm doing anything right. So negative 14 over 4. Negative 4.5. Put that down. Negative 7.5. So that is 7.5. So from right there, that is going to be 1.5. I think. But unless you're too busy texting or anything or not actually paying attention in this class, but you ain't heard from me. I ain't one to gossip. But yes, I will gossip about you because you are on your phone instead of actually doing the work. I have one person that actually pulled out a calculator. Thank you.
It was 52.
Huh?
52.
52.5? Thank you. Is that why you were on your phone? You were checking it? See? Look at that. See? Who's going to win? Right there. Now, let's pretend like we use the calculator a lot. Let's pretend like I need to actually know how to use this calculator. And the biggest issue I have every single year, people don't want to use my calculator. They're too lazy to actually get it out of their bag. So they use their phone instead. So once it comes test time, what do you think happens? You have no clue how to use the damn calculator. But can't bother to even bring out the calculator that I have given to you. So anyway, hit this right here, and my function was x squared, right? Hit enter. So delta x, which was 1 times f of, what was that, 1/2, right? Or 0.5? 0.5 is easy to put in like this. Plus 1 times f of 1.5 plus 2 times f of 3 plus 2 times f of 5. 52.5. Now, even though I did give a speech about it, so do we have to know how to use these calculators? Yeah. Are you allowed to use your phone on any of these tests? No. Am I going to teach you how to use a calculator during the test? Hell no. Am I going to tell you to how to even turn it on? Most likely not.
Why was the area so different?
Louder, please.
Why was the area so different the first time?
Why is the area so different from the first time?
Yeah.
Okay. yes, if we're thinking about our rectangles, and remember that statement I said? Okay, the first time, these are the left hand, right? So the left hand, if I were to graph this, actually, I will actually graph it. So, and so, let me see, menu, and that's what I want. And let's start at 0, and let's go to 6. And 5, 5. Okay. Now, from this right here,
It's gonna overestimate the negative part and then underestimate the positive part.
yes, why?
Reason why.
Give me the reason why.
There's gonna be part of it that's not accounted for because it's on the left side as opposed to up.
Yes, because it's the left side. And in this case, so that's why I did the picture here. So this is going to 6. So let's say all this right here. So it's saying all this is below. Pacho. Oh. Ooh, okay. I'll come by and see you next hour. Okay. Okay. All right, bye. Mm-hmm. Oh, alrighty then. Okay. Okay. Bye. All right, so there is an overestimation. So right here, this is 1 times -3.
Yeah, so you overestimate the negative part and underestimate the positive.
Very good. And since it was a left hand, once we were over here at 4,
It would, yeah.
yeah, this is where the rectangle is for 4. So it is very much an under.
And then the other one you said overestimate because
And look, let's see what it actually is. You ready? So, menu, analyze, and let's do integral. Lower bound, I'm going to start over at 0, so I'm going to enter 0. Upper bound, I'm going all the way to +6. So the actual area under this is going to be 54. So all this right here is negative. All this over here is positive, so when I cancel out the negative, I'm left with 54 there. So which one was closer to the actual?
But why was B closer? Because it was the midpoint?
Midpoint.
So like part of it was over and part of it was under?
Yep, on every single one. So that one is actually a better way of doing it, but it's not always going to ask you for the best way. It's not going to say, oh yeah, do it the best way. That's going to give you the most accurate. It's going to tell you specifically, do a left hand here, do a right hand here, do a midpoint here, or do a trap rule here. Trap rule is going to be 7/6, which comes out after 5.4. Because it's the same thing, but I don't know why it's in chapter 7, but still, it is. Okay, the theory is going up to it. All right, questions, concerns, complaints, conspiracy theories.
Can you show again? I find the actual.
Oh, from the graph?
Yeah.
Okay, so you ready?
Yeah.
So I'm going to go. Okay, watch this. You ready? Doc, letter.
When I erase the whole thing?
Yeah, erase the whole thing. And so, because I changed the window, I changed a couple things. So I'm going to show you start to finish, like how to actually get there. So, and if I was one of those people that, don't really pay attention, I might really want to pay attention at this time. And it was x squared minus 3. There we go. Hit enter. Now, do I have to change the window to do it? No, but did it help? Being able to see it, yeah, it kind of helps, right? So I only want to see the part that I'm going to use. So that my domain of this one would be from 0 to 6. So I go menu, window zoom, settings, change that to 0, change that to 6, and I already know the Y values get a lot bigger, so that's why I said 55. And we are trying to get the calculator to analyze the graph.
The integral.
Yes, we're analyzing the graph, so we're checking the graph for things. So I can do 0, min-max, intersection, inflection points, the derivative, there's my integral right there, which is the area under the curve. So, for those people actually following along and paying attention, integral refers to area under the curve. Okay. There we go.
Why do you want to find the area under the curve? And how is it useful?
All right, let's go to physics. I give you a velocity.
Yeah.
Okay. You're traveling at 45 miles an hour. That's your velocity. Okay. For an hour. Okay, that's an easy math to do, right? But if I do the integration of that, the distance traveled from 0 to 1 hour, the area under that curve, my graph, which is 45 miles an hour, right? Which is actually just a straight linear 45. So we are just finding the area, and that's the total distance traveled. So to find the integration of the velocity will give me the distance traveled. Okay? All right, so lower bound. Lower bound is where I'm starting at, which is 0. Enter. And if you notice, it highlights already where the line is for the upper bound. So if you're using the mouse will actually go different places. But I want it to be exact, so that's why I'm entering my numbers. 6. Enter. And this is from the end of these notes, but it actually goes along with these notes. So what we're doing is we're finding the integral from 0 to 6 of the function x squared.
I got 54.3. I might have missed a point.
Did you use the mouse?
Yeah. I think
Okay.
I might have just that little edge.
Yeah, so what you do is, instead, so when you actually do lower bound, just type, you don't have to select anything, just put the number.
Just put like 2.
Just put 0. Yeah, just enter 0, enter, and then it's going to change to upper bound. And go 6, enter. So this is what we're technically doing. We're doing the integration. My delta x is going to be the change, the thickness in that. So that's my x, my delta x right there, the thickness in between, and they're actually going to be infinite number of rectangles as I do this. So from 0 to 6, I go here to here. So let's integrate this. So x squared is going to give me x to the, what's the integration of x squared?
Integration?
Yeah, antiderivative.
Oh, okay. That would be x divided by 2.
Very good.
Wait, so, okay, it's also negative 3 x.
Yep.
So it's also called integration?
Yeah.
Okay.
So, but we started off with antiderivative because everything in math has its opposite. So the opposite of derivative, antiderivative, or integration. And so this is going from 0 to 6. This is what a definite integral is.
Why do you have to have the antiderivative?
Because I'm finding the integral. That's what this is. That's a symbol for integral.
So why do you need the antiderivative?
You'll see it in a second. Okay. All right. So let's plug these numbers in. So this is what this happens right here. So the top minus bottom. So it's going to be 6 to the third over 3 minus 3 times 6 minus the lower bound, which is 0 to the third over 3 minus 3 times 0. Uh, 6 to the third is going to be, what was it, 190. $196 over 3. I can't be right. Is it not 196, is it? 6 to the third?
Gotta do two.
18. 216.
Yeah, over 3 is.
That's 72. That's why. My God. 72 minus 18. What's it? By 4? Hopefully that's what the answer was, right?
Wait, wouldn't it be 5, 6? No, 5, 4, right?
Yeah. Okay. So, that being said, I'm going to leave off here. And we're going to pick up the next one tomorrow.
Do we need to write this?
Huh?
Do we need to write this ever?
You don't have to ever do anything. I don't think I can make you technically ever do anything.
Wait, so how does this work?
Okay, let Joseph finish his question.
Math-wise, like, would they make us write this statement out?
Oh yeah, no, this is actually just regular integration. This is definite integrals. But at this current moment in time, this is the reason that we actually got 54 for the actual area under the curve. The Riemann sum is an approximate of the area under the curve. Yeah. No. Definite integrals don't have C. And when we actually get into that more later on, I'll show you why.
How does it work?
How does what work?
How does it work?
Do me a favor, speak in English.
Okay, so you found the slope at the points.
No.
Yeah, because you found, or the anti. Oh, because it's not the derivative, it's the antiderivative. What does the antiderivative do? Like, what does it look like in this graph? Like, how can you find everything from that? What?
This is my function, right?
Yeah, you found the antiderivative.
Okay, antiderivative of the position.
Yes, which is
If it was a physics problem, it would be, yeah, that's going to be
But how
distance covered,
But how does it work?
just like that. Like, are you talking about in general what the definition of an integral is?
No, I mean like, how could you find the area under the curve by doing that? Like I don't know where it's applied.
Oh, let us get into that when we actually get into more fundamental theory of calculus. Right now, I only showed you this because I showed you how we got 54. That's the only reason why I showed you this. This is the end of the notes for this unit, this section. We're not doing that yet. We will get into it. So if you open the book, you can actually see it's the sum. We're taking the limit. We're taking the limit of the sum of infinite rectangles, but are infinitely small. So they're teeny tiny, infinitely small rectangles. The delta x is almost nothing. But I take the limit as I keep getting closer and closer to the limit I go to infinity, my number of rectangles, the addition of all those pieces together, it's the sum of the limit. Does that make sense? So yeah, so it's basically, I have little bitty rectangles, and then if you want to look at the notes for it, it actually has the limit function in there too. Okay. All right, so there you go.